Pleasure to introduce Nikolaj, who I invited. Nikolaj did his studies at Stanford University, and we were all very impressed. And then he went to Kestrel Institute, got involved in some startups, and now works for Microsoft Research. And while he may not have a broadcast quality voice, I can assure you that he can program while being driven at 75 miles an hour from Miami to FLAIRS, so he does have special skills, certainly from that. So what is he most well known for? His work at Microsoft is the Z3 theorem prover, automated reasoner for SMT logics, which is being used for program verification as part of the software engineering processes within Microsoft. And I quote that they have, with this work, found hundreds of errors that were in their software which had been previously undiscovered, and therefore contribute to the quality of Microsoft products. And that's what I guess we'll hear about now.
Okay, thank you, Jen. Yeah, I think you summarized the talk. I can go now. Anyway, so the official title of the talk is very long, but I abbreviated it to something like this. Use of automated theory proving in industry, where industry is Microsoft. I am a researcher at Microsoft Research in Redmond. Okay, so the outline of this talk is, it has 4 sections. So during the reception and other social interactions, I get a few questions about what is Microsoft up to, how does this work. So I'll give a little overview of how the context of which Microsoft research is. And in particular, I work in the Research and Software Engineering group called RISE. And this is a picture of most members from RISE. And then I'll give a short overview of automated theorem proving and satisfiability model theories. That's the acronym SMT. And so Z3 is an instance of an SMT solver, so it's an automated theorem prover that belongs to a particular category of provers. And finally, for the advertised content, I'll go through a few of the applications with the emphasis of those that are used in products. But the summary of the talk I would phrase as more or less like this, that there's a synergy or a virtuous circle between building research tools, developing core technologies, using the research tools into products, so moving them from research prototype stage, from the cottage industry to the bigger industry, and then that gives feedback to features to add, research directions to do. So this is very much the perspective of my work, and there is AI many places here, and I will make sure to mention this repeatedly. But of course, there's a lot of other research in AI that goes into Microsoft products, but I will not be going into this in any detail. Okay, so as for the 4 sections of the talk, first I will zoom in on where we are. So Microsoft Research has labs different places in the world, mainly in Redmond, New England, Cambridge, UK, Beijing, and Bangalore, and then there are labs in Silicon Valley and other labs around. However, research is a tiny fraction of the company. So Microsoft Research is a separate division, but employee-wise, there are about 1,000 researchers at Microsoft, and around 90,000 plus employees of Microsoft Corporation. So R&D division, research and development, is 40,000 people, and sales and support marketing is a bigger chunk. Every year we have a so-called Tech Fest, where we showcase our research prototypes to product groups. And this is a picture of the closed event. Tech Fest is a closed event for outside, but where employees go there and interact with the researchers, and either get a nice giggle from looking at what these weirdos are doing, or getting some inspiration, or shaking their heads and saying these researchers are way behind, So I used to work in the remote file systems group and developed a distributed file replication system. So I went to this tech fest at that point and saw a researcher who was proudly showing his research prototype, and he could replicate 50,000 files. And so I do that in half an hour on my desktop. So, but anyway, there is a good synergy between the research product or prototypes get into, you create contacts with the product groups and then get into synergies. This is a picture of the research and software engineering group, and our mission statement is to improve software development productivity. And that means several different things. We take as foundations logic for this, and then we do research in programming languages and program analysis. But there's a new, very popular and important trend in software engineering is to use empirical means of software engineering. So doing data analysis and analytics for the case of developing software products. Here's an example of a research tool that made it into Excel, the latest version of Excel. It uses what's called version spaces for automatically filling in tables in Excel. So the idea is that you give a partially annotated table that's shown on the left. So you have two columns, A and B column, and you give an example of how to transform the data in columns A and B into column C. So the transformation is to abbreviate Doe with D, but keep John. And then you hit this button called Flash Fill, and it figures out the pattern. And if it has enough samples to work with, it can complete the table to what you really intended. So it's under the hood. It's using AI technologies. So this is out of our group. We also have, if you get totally bored during the talk, you can go online and go to Rise for Fun, and here you can sample various of the research prototypes that we developed. So for each of these squares, there's an online demo behind the various tools that are mentioned. So AGL is an automated graph layout algorithm, and Daphne is a program verification system. Anyway, so that was the background. So the takeaway here is that we have, say, a cottage industry of research tools that get developed in our research division. And I will then now delve into specifically on automated theorem proving and the tool that I developed called Z3. So to put this in context, there are several flavors of symbolic engines for proving theorems. So in propositional satisfiability, you have propositions. In this example, you have ties and shirts, and you can create logical formulas around ties and shirts. And so this formula is satisfiable with the satisfying assignment that you are you have a tie. Sorry, you don't have you have a tie, but you don't wear a shirt. First order automatic theorem proving has a in the second example I give an instance of an algebraic property group theory, and you can use first order automatic theorem provers to prove theorems over group theory. In satisfiability modular theorem provers, they are distinguished by having background theories. So in this example, you have the symbol plus and minus and constants 3 and 1. So they come from arithmetic, sorry. So the point here is that SMT solvers have specialized algorithms for solving these special domains, where the special domain here is arithmetic. So I'll go through this in the next 2 slides as well. So the core deal in SMT is that they check formulas for satisfiability modulo a background theory T. And then they have specialized algorithms for them. And here's an example. It's a similar example paraphrased a little bit differently of a formula in SMT. And it combines arithmetic. So it has subterms that come from arithmetic in blue. It combines the McCarthy theory of arrays with select and store, and it's not Philip McCarthy's theory of arrays. It's McCarthy Senior. And then it has uninterpreted functions F. And if you look a bit closer at this, you can see that the formula is valid because if x plus 2 equals y, then y minus 2 is indeed equal to x. And then the select of store cancels out, and then 3 equals y minus x plus 1. Right? But the engines of SMT solvers know how to combine array theory and arithmetic and uninterpreted functions, each with their specialized engines, and then have smart ways of combining those solvers. So we build on progress in the propositional SAT solving, and during the last 10 years there's been quite a bit of progress on improving the power of SAT solvers, thanks to various algorithms, data structures, and heuristics. So this is a picture of taking benchmarks from a 2010 competition and then run the winners of each SAT solving competition and those benchmarks with a timeout. And we can see that the best SAT solver in 2010 could handle the first 40 problems within a few seconds, which was the timeout. This is where the best SAT solver in 2002 couldn't make it to. So a lot of progress in SAT solving. There's been a lot of progress in first-order theorem proving, and I would characterize it as mainly around algebraic problems, so math problems. So one distinguished theorem is the XCB theorem of that there's a single axiom for equivalence. But in recent years, there's been quite a bit of progress in reasoning about knowledge ontologies. So there you have gigabytes of formulas, and the challenges around that is selection functions. And these are different problem settings than SMT solvers, but I believe that we also can claim some advances in this area. So the story of SMT solvers starts from the mid-70s and goes up with some slowly in the 80s and 90s, and then had quite a bit of progress in the last 10 years thanks to running competitions in this style similar that Jeff has run for first-order theorem provers during the last 20 years. But there's been quite a bit of action in this area. One thing to note is that the core of our SMT solver, Z3, contains a SAT solver, which is about 15,000 lines of code, but it's much more than a SAT solver. So another 280,000 lines is the specialized algorithms. And so another thing to keep in mind is that so in SMT and theorem proving in general, we do symbolic reasoning over domains that have high computational complexity, and start with propositional SAT being NP complete, and then go up to quantified Boolean formulas, effectively propositional logic, first-order logic being semi-decidable, and then highly undecidable classes. But the point is that in practical problems, we claim that they often have structure that can be exploited. So exploiting this structure is much more important than anything else. So a lot of what goes in indexing data structures and algorithms is to leverage the problems we get from the applications. To solve these, there's quite a bit of structure to employ. Okay, so now on to propaganda for my theorem prover Z3. So if you don't remember anything else, just Z3 is... okay, so here's some Microsoft tools using Z3. They are developed in the... most of these are developed in the software engineering group, and then there are other groups in Microsoft Research Cambridge that develop tools. They are practically all around program analysis, testing, and verification. So it's around software development, in other words. They come in different flavors. So some are old school program verification tools. You take a program, you annotate it with assertions and variants, and you check these. So the Bookie tool is a verification condition generator for such tools. It's a backend for some of the programming languages you can feed in. So the verifying C compiler takes so VCC takes C programs as input, feeds them to Boogie, and then feeds them to Z3. Daphne is a different language. It's a verification-oriented programming language, and it also feeds into Boogie that then generates formulas. And then there are so-called software model checkers that automatically check properties of software. So SLAM and Yogi are examples of these. And then there are testing tools, program tools that generate tests in both PEGS and Sage. And then we have model-based tools where you start with a model and derive a system, and Formula is such an example. And there are also some other cool tools, not from Microsoft Research, that use Z3, and some of them have interesting logos. The important part here is that for every tool uses a set of different features, but the sum of the parts, so they can go in and say implement a special purpose reasoning engine, but they get to leverage it. But the sum of the interaction between the parts that we can provide with the general purpose Z3 helps them from inventing a special purpose wheel here. They also use different APIs. Some want proofs, other ones models, and some want to simplify formulas. Actually, Isabelle uses the Isabelle theorem prover uses proofs. So, as I said, the important part in SMT solvers is that they combine specialized algorithms, and they do so efficiently. So we call this a combination of little engines of proof. And so example engines are simplex solvers and quantifier reasoning engines, bit vector arithmetic, quantifier elimination algorithms. You can, as I mentioned before, if you are online, you can go to Rise for Fun, and there's a Python front end for Z3, and you can use it to solve your Sudoku problems or other leisure activity, or 8 queens. And so these are educational problems to show how to formulate constraints and solve them. What people say about Z3? Well, I'd like to say that it's a powerful tool. Some even say that it's a crown jewel. I don't know why, but and then we had a German colleague who pointed out that it's not a car, and but it's fast. And then your favorite conference management system called EasyChair, the creator of EasyChair, reminded me that Z3 is smarter than me because I sent an email to him and from EasyChair, and of course he would get that email from EasyChair as well, so I didn't have to remind him about that. Okay, so it's cool and nice and all that. Some of the interesting newer features in Z3 are algorithms for solving the existential theory of reals efficiently. So here's the key idea, is to use partial solutions to guide search. So search does backtracking, but if you don't do proper learning during backtracking, your search space is immensely high. So the key is to get as precise lemmas, or as precise no-goods, as the AI terminology is, for failed branches. So here's an example where you have three inequalities, and the problem is to figure out whether the conjunction of these three inequalities is satisfiable, whether they have a solution. And as I've drawn them, we can visually see that the green area is, everything in the green area is part of the feasible region. But the problem is, of course, to find the feasible region by search. Now, so suppose we guess that x is half, then we can see that no matter what value of y we assign, there will be no solution. So there the trick is get an explanation why x equals a half is a bad choice. It turns out that you only need the two blue constraints to explain why x a half is a bad choice. You don't need the constraint on the right, the orange constraint. So what this means is that you generate a minimal explanation using just the minimal sets of constraints that were shown that the current choice is infeasible. And that has a tremendous advantage on top, as opposed to what people have done so far, to use complete quantifier elimination procedures for checking just feasibility of reals. Here's another newer part of Z3 that I'm involved with, which is to reduce program verification or symbolic model checking to theorem proving. So here's McCarthy's 91 function, and it's still not Philip's. It's also John's 91 function, and I use this because it's you can write the function in 2 lines and the assertion in the 3rd line, and it's slightly non-trivial because it calls itself twice. But you can formulate checking this assertion as a theorem proving problem, as a satisfiability problem. So if you rewrite the program as a relation between input and output, so now the McCarthy is no longer a function that takes one input, but it's a relation between input and output. And then you write down the equations for the program using Horn clauses. Then the claim here is that these set of Horn clauses are satisfiable. They have a solution if and only if the assertion in the program is correct. So now the task is to find solutions over these Horn clauses, and so that's a very general framework for doing automatic software verification as theorem proving. Z3 is shared source, and you can go online and download both binaries, but also the source code, and modify it if you feel the urge to. So it's on Codeplex, z3codeplex.com, and so when we publish papers and make some outrageous claim about our algorithms, then one can go in and look at the source code and check. And this is similar to how progress in SAT solving has gone on. You look at the source code because there's so much going on, even at the low level. Now to the industry applications, as finally promised. So the point here is divide and conquer. So Z3 is a low-level backend logic engine, and then the conquerors have tools that map their problems into Z3. So we had a project that ran from 2009 to 11 on verifying a large portion of the Viridian hypervisor. So the hypervisor is is essentially an operating system. It's a small one that takes 100,000 lines of C, and then it can run guest operating systems and it's used, for example, in Azure data centers. So it mimics the hardware. It pretends that each of the guest operating system owns the hardware. And then we verify safety of the hypervisor, that it correctly mimicked the hardware. Now, so that was a exercise, adventure in standard or traditional program verification, where you give assertions to program and then run them through a check or a verifier. And so on the top so you have the top of the food chain are the people who do the program verification, and this is how they look like. They're popular and beautiful. Rustan is one of my colleagues who does program verification, and others get best paper rewards. And then at the low level, those who get conquered are the proof plumbers who provide the theorem provers. So we have whiteboards behind us. So these are the developers of Z3, Leonardo and me and Christoph Wintersteiner. But okay, yeah. So and then we read books with handbooks of satisfiability, but okay, there's still some hope. Anyway, so here's another example of traditional program verification, the Verve operating system. So that's an example of a microkernel that was verified. The particular invention here was to cast most of it as typed assembly code that could be type checked. Then you have much less to verify. A very impactful application of Z3 is for fuzzing and test case generation. So this is a new subject, and we have two tools, Sage and PEGS, and they find security bugs before the black hats hackers do. And Sage is particularly impressive, and we run it internally on several servers continuously for Office and Windows applications, and which we estimated that it's the largest solver use of a theorem prover so far. We've done 3 billion plus constraints. We've gone through Z3 via Sage. There's some nice, we get some nice bug reports when Sage reports a bug to a developer, and then he looks at this bug sequence that you find, that the tool finds, and so you basically have a very intricate sequence of events that all have to align to hit the buffer overrun. So here's how it works. Here's how symbolic test case generation works. So consider this GCD algorithm, and you want a trace where the loop is executed twice. So what you do is you unfold the trace in single static assignment form. So that's done here. So now it's a logical formula, and then you can solve for that logical formula and get back a value that satisfies that formula. So now the values for x0 and y0 are these inputs that will steer the program in the loop twice. So that's how it works in a nutshell. And then you feed it in a feedback loop with a theorem prover that finds new paths and solves for these. last application, network policies. So the highlight here is that configuring and managing networks in the cloud, in this case it's Windows Azure, is incredibly complex, and most of the errors that happen according to an internal estimate is based on configuration problems. So when you change configurations, you introduce bugs. And so what do these configurations look like? These are firewalls. So there are firewalls put on firewall policies put all over the network. So this is how one of these policies look like. So a firewall policy is a sequence of rules, and they tell you which package, which IP packets to pass and which ones to drop. Now, you can take a rule and view it as a formula. So a rule corresponds directly to a logical formula. It's a predicate that says whether a given packet matches the rule. So I took two examples, an allow and a deny rule, and wrote them as a logical formula. And now you can take a policy and so a sequence of rules, and you can formulate them as logical formulas. And now, so the point is, it's very easy to take policies and map them to logical formulas, and then when you have a theorem prover that can process them, you can leverage that to ask queries about these policies. So what we do with Azure is we check differences, we do semantic differences between policies. So we basically ask whether the XOR of two policies is feasible. And when they're feasible, we get satisfying assignments, and some of the secret sauce in this tool is to get sets of satisfying assignments in one go. And I won't have time to go into that, but that's to give you a highlight of another application of theorem. Okay, so the summary is as follows, that there's a ecosystem of tools and technology. So in my context, I'm a researcher, so I developed the tool Z3, and we collaborate then with other researchers who have a cottage industry of developing research tools. Several of these get used in products, and then there's a feedback loop on developing new technologies. Thank you.
Last question.
Is there any integration of TFX with automated builds?
Sorry?
Is there any integration of TFX with Team Foundation Server?
Whether there's an integration with Team Foundation Server.
Yeah.
In which way? So Team Foundation Server is like...
I'm trying to understand at what level does it check does it do the verifications with like C# level or the ILs? I'm trying to see where the integration point would be for automated builds.
So for the test case generation, so there are two tools. PEX does for .NET code. So you can run PEX in Visual Studio, and it's aimed for developers. Sage runs on binaries, so you give them a x86 executable or x64 executable, and then the requirement on the executable is that it can read a file. So you start with a seed file, and then you run that executable. Now the technology behind Sage is that it runs in a virtual machine like infrastructure that records the instructions that get executed, and those instructions are fed to the theorem prover. Yes?
Microsoft produces some well-known architectural simulations of a number of products. Is this product used in those?
Galileo, is it Galileo or?
I forget the names of them.
The simulator.
Yeah.
No, yeah. So that's actually a good question. It could be. we've been tempted to see if we could use Z3 in context of a simulator, but we don't have any product or tool for that. But it's a tempting idea.
Yes. Is the C3 open to or free also for commercial applications? If I want to build something commercially, I want to use C3.
It's actually for sale on the Microsoft Store for commercial.
I'm just curious. I mean, and then we can buy it for.
No, you can. It's for commercial. It's for sale. You can
Okay.
you can pay, and for academic it's free. Just, there's so we yeah. So it's you're not prevented from using that.
If you have enough money, you can use it.
It's
Okay.
cheap.
Any more? All right, thank you, Nikolaj.